A flash of light splits the night sky. A deafening crack of thunder echoes through the remote forest canyon. And then, an unnerving silence returns, broken only by the sound of a passing breeze. Hours pass, days pass, maybe even weeks. Then, a hiker on a distant ridge spots it. A thin, white plume of smoke lazily rising from the canopy. A wildfire has been born, not in a sudden explosion, but from a secret that has been smoldering, hidden from sight, since that storm passed. How can a fire hide for so long? And what makes a single bolt of lightning, out of millions, the one that sets a landscape ablaze? Welcome to G Fun Facts Online. Today, we're unraveling the fascinating, complex, and dangerous science of how lightning ignites wildfires. You'll learn that it's not about the spectacular, instantaneous blast of power, but about the quiet, persistent glow that follows. To understand this, we first have to get one thing straight. Not all lightning is created equal. The sky is buzzing with electrical energy. Globally, there are an estimated 46 lightning flashes every single second. But the vast majority of these are harmlessly discharged within a single cloud or between two clouds. They never reach the ground. The ones we're interested in are called cloud-to-ground or CG lightning. But even among these, only a small, specific subset possesses the right characteristics to become a fire starter. A typical lightning strike is an event of almost unimaginable power. The channel of air it carves through the atmosphere is superheated to around 30,000 Kelvin. To put that in perspective, that is 5 times hotter than the surface of the sun. This rapid extreme heating generates the brilliant flash we see and the explosive expansion of air that we hear as thunder. The whole event is a multi-stage process, but let's focus on the most visible part, the return stroke. This is what you think of when you picture lightning. A channel of charged particles zigzags down from the cloud, and when it gets close, an upward moving streamer of opposite charge reaches up from a tall object, like a tree. When they connect, a massive surge of current, the return stroke, flashes back up to the cloud at nearly 1/3 the speed of light. An average negative CG strike, the most common kind, carries about 30,000 amperes of current. You would think this incredible blast of energy would be the fire starter, right? But ironically, it's often too powerful and far too fast. The entire return stroke lasts for only microseconds, millionths of a second. While this is enough energy to cause immense mechanical damage to a tree, instantly boiling its sap and generating explosive steam pressure that can blow the bark clean off or split the trunk in two, the heat dissipates almost instantly. The fuel, the wood and needles, simply doesn't have enough time to absorb the energy it needs to reach its ignition temperature. The real architect of fire is a much less dramatic, but far more important component of the lightning flash, the long continuing current, or LCC. Following that initial, brilliant return stroke, some flashes maintain a lower level current. Instead of 30,000 amperes, it might be in the range of 100 to 1,000 amperes. But the key is that it can flow for a much longer duration, from several milliseconds to, in some cases, hundreds of milliseconds. That's 1,000 times longer than the return stroke. Think of it this way. The return stroke is like a flashbang grenade, a massive, instantaneous explosion of energy. The long continuing current is like holding a blowtorch to a piece of wood. It's this sustained drip feed of thermal energy that is the primary culprit in most lightning-caused fires. Laboratory experiments and field observations have consistently shown that this prolonged heating is what's necessary to overcome the cooling effects of moisture in the fuel and bring the organic material to the point of ignition. In fact, studies confirm that flashes with a continuing current lasting more than 10 to 40 milliseconds have a significantly higher probability of starting a fire. Now, let's add another layer of complexity: polarity. About 90% of all cloud-to-ground strikes are negative CG lightning. They transfer negative charge from the cloud to the ground, and are often characterized by multiple return strokes in a single flash. While only about 20% of these negative strikes feature a long continuing current, their sheer frequency means they are still responsible for a significant number of fires. But then there's the other 10%, positive CG lightning. These are the true heavy hitters. They originate from the positively charged upper regions of a thunderstorm cloud, and they often strike miles away from the storm's core, in areas that might not even be experiencing rain. These are the infamous bolts from the blue. Positive strikes are typically much more powerful. An average positive strike can carry double the peak current of a negative one, and more importantly, they are far more likely to have that all-important, long, continuing current. So, when you assemble the perfect lightning strike for starting a wildfire, it's most often a positive cloud-to-ground flash with a long, continuing current, delivering a sustained jet of thermal energy into a receptive fuel bed on the ground. That brings us to the second half of the equation. A lightning strike, even the perfect fire-starting kind, cannot ignite a fire without a receptive fuel bed. The forest floor isn't a uniform carpet. It's a complex mosaic of organic matter, and its potential for ignition is governed by a handful of absolutely critical factors. The key chemical process we need to understand is pyrolysis. This isn't burning in the traditional sense. It's the thermal decomposition of material in the absence of sufficient oxygen. When you heat complex hydrocarbons in wood, needles, and leaves, they break down into smaller, flammable gases. It is the ignition of this cloud of flammable gas that actually produces a flame. And the single most important factor that stands in the way of pyrolysis is fuel moisture content. Water has an extremely high capacity to absorb heat. Before a single particle of fuel can reach the temperature required for pyrolysis, around 600 degrees Fahrenheit or 315 Celsius, any water it contains must first be heated to its boiling point and then vaporized into steam. This process consumes a tremendous amount of the lightning strike's energy, effectively stealing it from the ignition process. Forest fuels are generally divided into two categories based on moisture. Dead fuels, things like grasses, fallen needles, and small twigs, have a moisture content that is highly responsive to the surrounding atmosphere. In hot, dry, and windy conditions, their moisture content can plummet, making them readily available for ignition. Fire managers often cite a dead fuel moisture content below 20% as a threshold for a significant increase in ignition probability. Live fuels, on the other hand, such as green leaves and living branches, have much higher moisture content, often over 100% of their dry weight. Igniting them directly is extremely difficult. However, under conditions of severe, prolonged drought, even their moisture levels can drop enough to contribute to fire spread. But it's not just about how wet the fuel is. It's about what it is and how it's arranged. Forest fuels are not uniform. Their size, shape, and arrangement on the forest floor dramatically affect their ignitability. There's a crucial difference between fine fuels and coarse fuels. Fine fuels, like pine needles and dry grass, have a very high surface area to volume ratio. This means a large portion of their mass is exposed to the air and to heat, allowing them to heat up and lose moisture very, very quickly. This makes them the most common initial point of ignition. In many documented cases of lightning fires, the first material to be ignited is the duff layer, the thick, spongy layer of decomposing needles and other organic matter right on the forest floor. Coarse fuels, like large logs and stumps, require much more prolonged heating to ignite. They have a low surface area to volume ratio, but once they do catch fire, they can hold that heat and smolder for extremely long periods. Finally, the compactness or bulk density of the fuel bed is crucial. A loosely packed bed of fresh pine needles allows for excellent oxygen circulation, which can aid flaming combustion. However, a denser, more compacted fuel bed, like that deep duff layer or a peat deposit, is more prone to initiate and sustain smoldering combustion, a key process in those mysterious, delayed ignitions. This is where the story gets really interesting. The initial ignition by a lightning strike is often not a dramatic burst of flame. More commonly, it's the beginning of a slow, flameless, and often hidden process known as smoldering combustion. Smoldering is a low-temperature form of burning, where oxygen from the air reacts directly with the surface of a solid fuel, like char or peat. It's the exact same process that allows a charcoal briquette to glow red for hours after the initial flames have died down. It produces very little visible smoke and no flame, but it generates enough heat to sustain itself and slowly consume fuel. Smoldering is the critical link in the chain of many lightning-caused wildfires, particularly those that exhibit that long delay between the strike and the appearance of a visible fire. This delay is known to fire scientists as the holdover period. A fire can be ignited by a lightning strike and then smolder for days, or in some documented cases, for weeks, before it is finally detected. Imagine a positive lightning strike with a long continuing current hitting an old, dead tree. The energy travels down the trunk and into the root system, which is embedded in a deep, dry layer of duff and organic soil. The duff begins to smolder. There isn't enough oxygen for it to burst into flame, but there's enough fuel and insulation from the soil above to maintain this slow, creeping burn. These subterranean fires can move along old root channels, consuming organic soil, and are notoriously difficult to detect and extinguish. They can even survive moderate rainfall. This is because when very dry organic soil is heated, it can become hydrophobic. It literally repels water. Rain that falls on the surface might simply run off, instead of penetrating down to the smoldering front. So you have this stealthy, underground fire, a hidden coal, just waiting for its moment to erupt. This critical and dangerous tipping point is called the smoldering to flaming transition, or STF transition. It requires three key ingredients to happen: a sufficient supply of those flammable pyrolysis gases from the heated fuel, enough heat being generated by the smoldering itself, and a sudden, significant increase in oxygen supply. Often the trigger is a simple change in the weather. An increase in wind, for instance, is the classic trigger. As the wind blows over the ground, it can force more oxygen down into the smoldering fuel bed. This intensifies the smoldering, which increases the temperature and the rate of pyrolysis. Suddenly, there is a large enough cloud of flammable gas mixed with enough incoming oxygen. It ignites, and what was a hidden glowing coal erupts into a visible flaming fire that can then spread with frightening speed through the lighter surface fuels like dry grass and leaves. A sharp drop in humidity or a spike in temperature can also contribute by drying out all the surrounding fuels and making them more receptive to the heat radiating from the smoldering site, facilitating that transition. Of course, this entire elegant and dangerous process from bolt to blaze doesn't happen in a vacuum. It is ultimately governed by the surrounding environment, the weather, the topography, and our rapidly changing climate. The most dangerous storms for fire ignition are often called dry thunderstorms. These typically happen when high cloud bases and a very dry lower atmosphere cause most of the precipitation to evaporate before it ever reaches the ground. The result is a storm that delivers dozens or hundreds of cloud-to-ground lightning strikes without the quenching effect of rainfall. It's the worst of both worlds. However, as we learned with holdover fires, even a so-called wet thunderstorm isn't a guarantee against ignition. Research has shown that smoldering fires can be initiated and survive even with rainfall of up to 7.7 millimeters, or about 3/10 of an inch. The fire simply waits in the duff until the sun and wind dry everything out again days later. The shape of the land, the topography, also matters immensely. Lightning is a game of probability, but it is more likely to strike high points on the landscape, like ridges and peaks. Once a fire starts, it also tends to burn much faster uphill, as the slope acts to preheat the fuels above the firefront. In the northern hemisphere, south and west-facing slopes receive more direct sunlight throughout the day, which leads to lower fuel moisture and a higher overall risk of ignition. And finally, we must address the elephant in the room, a changing climate. There is now a strong body of evidence showing that climate change is actively increasing the risk of lightning-ignited wildfires around the world. Why? Warmer global temperatures lead to more energy and moisture in the atmosphere. This increases atmospheric instability, which is the engine that generates thunderstorms. More thunderstorms mean more lightning. Projections for the western United States, for example, suggest a significant increase in the number of lightning days per year by the end of the century. But it's a double whammy. At the same time, those hotter and drier conditions are creating more receptive fuel beds and significantly longer fire seasons. This means that when lightning does strike, it is far more likely to hit fuel that is ready to burn, and the resulting fire has a much longer window in which to grow into a large, uncontrollable event. It's a dangerous feedback loop where a warming world creates both more ignition sources and more flammable conditions. So, the science of wildfire ignition by lightning reveals a remarkably intricate process, a perfect storm of atmospheric electricity, fuel chemistry, and environmental conditions. It's not the brute force of the lightning bolt, but the persistent, glowing heat of its continuing current that provides the spark. It's not just a patch of dry grass, but the complex, layered, insulating structure of the forest floor that provides the fuel and the hiding place. And it's often not an immediate explosion of flame, but a slow, hidden smolder that allows the fire to survive, biding its time, waiting for a simple gust of wind to erupt. Understanding this science is more critical than ever. As our planet continues to warm, the conditions that favor these natural ignitions are becoming more frequent and more widespread. The delicate balance is shifting, turning what has always been a fundamental ecological process into a growing and devastating threat to communities and ecosystems worldwide. By unraveling the secrets of the spark and the smolder, we can better predict, prepare for, and hopefully learn to coexist with one of nature's most powerful and elemental forces. Thank you for tuning in to G Fun Facts Online.